Welcome to a session amusingly called The Big Ones. And I can assure you that refers entirely to the scientific content of the data which is emanating from these important institutions around the world. Our first speaker will be known to many of you. It's Deputy Head of IT at CERN, David Foster. He's responsible for the international network strategy for LHC. And he's going to talk about some particularly interesting networking, which is the result of the expansion of the CERN data center. So, welcome, David.
Thanks, John. Okay. Well, good afternoon, everybody. I'm glad John clarified the title of the session as the big ones. I was afraid he was referring to the dietary habits of the speakers. But so I'm going to sort of change gears a little bit. It will be fairly traditional for me to come and talk to you about LHC networking in general, the LHC optical private network, the new sort of emerging project LHC1. And you can go to lhc1.net to find out what's happening in that space, which is the connectivity between Tier 1 and Tier 2 centers, which is another big activity that will be familiar to many of you because a lot of people are involved in that. But what I thought I would talk about today is something that's been announced in the press. It's the expansion of the CERN data center. And it touches on a number of things that we've been discussing during the course of the week so far. So I think I'll try to make this as informative as possible. Now, I should say that I acknowledge all the material here from my colleague Wayne Salter. I've not been personally too much involved in this whole activity, but I wanted to nevertheless expose to you some of the things that have gone on in the last few years around the thinking about how we will expand the data capacity at CERN. So I'll go through a bit of our own sort of personal brief history of remote hosting, the call for tender that we did, the selection of the site, and where we are and where we're intending to go. So the issue was how to provide the resources once the CERN data center is full. It's a 3 megawatt data center built in the 1970s. So it's got a lot of sort of legacy to it. And the big problem at CERN is actually getting now more power into that data center. It requires digging up the whole site, and that was considered to be not a feasible thing to do. So we for several years now, looked at all sorts of different options. We did a conceptual design study for a new building on the French part of the CERN site. Actually, there's another little anecdote I should tell you about that. The CERN data center, CERN itself, there are 2 main parts to the site, one which is truly in France and one which is in Switzerland, but actually spans the Swiss-French border. So there's a fence around it and there's a logical border in the middle. But it really is managed on one side by the French authorities and the other side by the Swiss authorities. And the data center itself is actually in France, technically. It's on the Swiss side of the CERN site, but it's technically in France, which has a few interesting side effects. The one is that the Swiss Géant Pop, which is hosted at CERN, is actually in France, technically. And the second is when the French ship their equipment to the CERN data center in France, they have to equip it with Swiss plugs. So we are fair to everybody in this world. So we did some conceptual designs, we looked at this, and of course it's a major expensive job to put up a new data center. At the same time, there was a lot of interest from Norway to provide a remote hosting facility. And we had a lot of discussions, but really the second sub-bullet here explains the problem. The slow-moving politics just meant it never happened. It never really gelled. So what did take place is that we did a call for tender from all of the member states. So the 20 CERN member states. And we asked them all, we said, you know, we have this idea, we want to actually have a data center as a service. So it's really a sort of infrastructure as a service play. And, you know, would you be interested? So what would we use this for? So this allows me to clarify something else. There is, in fact, a Tier 2 center in Hungary already at the Vigna data center. And this, what CERN is doing has nothing to do with any of the other activities at the LCG. It doesn't replace any functionality. It is an extension of the existing data center. So it'll be used for two things. It'll be used to extend physics and non-physics activities into the new location, and it'll be used for business continuity. So it'll be used for backup and replication of various types of services. So it really should be considered as a sort of long extension to CERN. We preceded this by saying, would we know how to actually manage and run services on a remote site? So we took the opportunity to actually buy some hosting space in Geneva, somewhere where we could easily drive to and easily go down and sort out problems. And we did that since 2010, and that's been rather successful. So that gave us a bit more confidence for actually going ahead and saying, yes, actually it's feasible. We will be able to change our operational models. We do understand how to evolve the cloud, the internal cloud, the private cloud type virtualized infrastructure. We will be able to do this. So we did this sort of little pre-experiment, and in fact, this is still running. So we do run several services down still in the data center in Geneva. So we did a call for interest at the CERN Finance Committee, and we wanted to be able to get some idea. Was this a completely silly idea? What would we get for 4 million francs a year? Would we get any sensible offers? Is it technically feasible? Is it interesting? Will people respond at all? So it was very surprising. We got more than 23 proposals. So this was not the call for tender yet. This was just a sort of an expression of interest. And we saw this massive variety of solutions, from existing centers to non-existing centers to future plans, people offering 2 megawatts up to 5 megawatts, and clearly a lot of differences in the tariffs of electricity. So it was clear that there was going to be a big range of responses when we actually did the call for tender. But again, it sort of was a proof point that, yeah, this is actually something interesting. People will be very interested in responding to a tender, so we should go ahead and do it. So we had many visits and discussions. And in 2011, we started with the tendering process. A number of new consortia in different countries were actually created expressly to reply to this call for tender. So that was that was another interesting side effect. It hit a note that people understood in the sense that they were all interested now in maybe, yes, this is a new sort of interesting business direction to go in, and having the CERN data center would be a sort of flagship application. So we sent out the call for tender in September, and we tried to make it as generic as possible. We did not want to specify how the data center should be built, because it was not to be a building owned by CERN. This was really an infrastructure as a service. We wanted them to provide us a service, so we didn't want them to be constrained as to how they should do it. We decided on a 7-year contract length with at least CERN equipment in a separated area with controlled access. Fully configured racks, so we wanted to just be able to have equipment placed straight in the racks with redundant PDUs, and essentially a set of services which we couldn't do remotely. So we want somebody there to take the equipment, unpack it, put in the cabling, smart hands and eyes for the operation, all the way through the life cycle. So into repair, stock management, and eventually retirement, decommissioning, retirement, extraction of the equipment, and disposal. So we wanted this complete set of services. We wanted also to make sure that the real-time monitoring info would be actually provided back into the CERN monitoring system. This is to be a remotely managed center. There'll be no CERN personnel there. We won't hire people there. We'll treat it really as a remote service. Installation of cameras, yes, for some security, but mainly what we also included was a list of typical equipment that we might actually have in order for them to adjudicate what the costs would be for them of taking such types of equipment, taking it out, putting it in racks, cabling it up, and eventually disposing of it. So we didn't specify exactly the equipment, but really a typical set of things that we would ship so that they could actually cost this and understand what it would mean for them. In addition to the CPU and disk, there of course is a star point for the networking, a certain number of racks, the patching we would require, and for the switches. And for the external connectivity, this was an interesting problem because we somehow wanted to factor into the adjudication the cost of networking. So what we actually did is we utilized the fact that the Xeon network is sort of omnipresent throughout the member states and said, okay, you should also include the cost of the connection from the nearest Xeon POP, whichever one you choose, to the data center that you are proposing as part of the overall cost of the price. So that enabled us in some way to factor in local networking costs, whereas the international networking costs from CERN to a particular Xeon POP is essentially a fixed price wherever that is. So that's a sort of constant in the equation. So what we wanted to do is to factor into the adjudication the variable cost of getting from the Xeon POP to the data center. Now, there are a number of SLAs, and this ended up as being quite complicated nevertheless. An SLA, yeah, you have to have some form of expectation setting. So it's called an SLA, and technically there are penalties for not actually conforming to the SLA, but this has to be managed fairly carefully. In this particular cable, this is the plan of how we intend to actually ramp up the power. Don't look at it too closely because it's a little bit confusing. But essentially, you see that in 2013, we start off a fairly gentle sort of level through 13, 14, 15, 16. Then there's some equipment refresh in 18, and there's some more equipment added, which is why there appears to be a little bit of a dip here. But in fact, in the total power consumption, it's not actually a dip at all. And so it ramps up to about 2 to 3 megawatts. So it essentially doubles the capacity of the CERN data center, starting with 100 kilowatts or so, and then going up steadily over time. So we'll sort of feel our way and put more equipment there as we gain more experience. There are some particular constraints, of course. Timings are all very important. So in this particular case, new equipment will be shipped. It has to be installed within two working weeks. For the networking, we anticipate things like this: 10 racks for LAN routers, 2 racks for WAN. Again, everything has to be unpacked, delivery. So the SLAs all specify the timings for how long each of these different operations should take. And the networking also has a lower growth, but nevertheless a constant growth over time. Of course, there is the reliability. So now we get into the issue of the power and the power redundancy. And because we didn't want to actually specify how the data center should be built, we actually tried to specify what it should be as a service. So equipment interruption, sort of fairly typical numbers. What the UPS should provide in terms of the amount of capacity for running the equipment, the installed equipment that's there, so a 10-minute buffer at least. Operating temperatures, well, that's only so that we don't actually cook the equipment. I mean, they must be able to guarantee that if the power goes off, that there is a mechanism to ensure that the temperature does not rise in the CERN part of the data center above certain thresholds. They must be able to provide real-time monitoring parameters back to CERN so we understand what's happening, what's the power usage, capacity of the UPS systems, infrastructure alarms, of course, temperature, humidity, so all of the typical measures that you would you would require. So this is all requirements in the technical specification of the tender for what the data center should be capable of doing, or what the service should be capable of providing to us. And of course, for the full life cycle, all equipment will be removed and prepared for disposal and shipping within a period of time. We have a set of typical failure rates of IT equipment that, of course, we've understood over many years. So this allows you to cost the amount of interventions, and we talk about how many there will be for each type of failure, and that again allows the bidders to actually put in their estimates of their total cost. In addition to that, of course, there are the repair times, so there needs to be a contract for 24-hour intervention, and what this actually means in terms of replacing disks. So it's largely equipment replacement that we're insisting on. People should be able to replace disks, be able to replace RAID controllers, and be able to extract other types of equipment for longer-term repair. And of course, the number of interventions we expect to have on switches and routers per year. So the whole technical spec ended up quite long and quite complicated, but based upon our sort of practical understanding of where we thought the level of failures and interventions would be required. In addition to that, of course, there is the sort of the required hands and eyes, so we require people to go and actually intervene on a sort of case-by-case basis on equipment on demand. So we estimated the number of interventions we would ask them for, 5 per 100 IT systems and 10 per network equipment per year, something of this time, and what the intervention time would be required. And although we say penalties defined for non-respect to the SLA, it is a contract, so there will be contractual clauses related to that. But mainly the intention is for everybody to understand what the expectations are, and indeed what the implied costs are for the hosting center. So this is what we got back. In the end, we got back from these countries quite a number of bids. A few consortia in individual countries declined, and some actually placed a bid. You see from Norway, which is extremely active in the number of consortia, even though 4 consortia in Norway declined, 5 actually bid nevertheless. So that was it shows that the level of interest, nevertheless, in Norway has grown considerably over the last few years. So there was some corrections. There was the usual process that we have of going through, answering questions, reviewing the technical compliance, all of this sort of business, and then a number of meetings were held with the 5 most likely consortia to really ensure that they'd understood what we had asked them, they had correctly bid, and that they had understood the costs, and yeah, that corrected some errors in their understanding. So the whole bidding process took quite a long time, because it was very important to go back and keep rediscussing with them what the issues were, did they really understand what we meant, and so on. And then eventually, on the 14th of March, the final decision was taken. And of course, everybody knows by now that this is the Vigna data center in Budapest. So it's a fairly large location, easy to reach from the airport. It looks very good. It is an area that is dedicated for research institutions. It is where the Tier 2, or it's part of the consortium where the Tier 2 is in Hungary. So that's also a plus. It's a building that is being refurbished. This is what it should look like at some point in the future. We will not be the sole occupant of the building. There will be CERN plus some others, but we will be in an isolated area. It's quite large in general. It fully satisfied all of the technical requirements in terms of what we needed for power, redundancy. They can guarantee the service. That all seems to be well understood, and there is a sufficient technical support for them to offer all of the additional services that we actually need on top of the basic technical infrastructure. Now, what we will do is we will look at this in two ways, as I said at the beginning. First, for an extension of the CPU and disk capacity required for the LHC computing, but also as a business continuity infrastructure. So we're now looking at how we will do that, how much emphasis we will make for backup, for load balancing, for reinstallation, and everything will be based upon the fact that we'll virtualize all of the services. So we'll be able to move the services backwards and forwards. So that's really the long-term goal. But it is something that is just in the process of being, I would say, understood by us. We wanted to make sure that that for networking that we actually had a sufficient level of redundancy. We talked about the two 100 gig links, but in actual fact, they both go to the same, or they would both go to the same Xeon POP in Budapest. So what we've actually decided to do is to make sure that we have POP redundancy. We will take one 100 gig circuit from CERN through Xeon, and then on to the Vigna data center, and then we will contract with a commercial provider for another circuit that will be completely redundant from the Xeon circuit, not only in terms of fiber, but also in terms of POP location. And not only in terms of POP location in Budapest, but also at CERN. So one of the things that we now have to do is to establish an independent network hub at CERN, independent from the computer center. So we're sort of really building this out in multiple dimensions to make sure that we actually now, if we're going to do business continuity, that we not only have redundancy in terms of services, but that we have really good redundancy in terms of networking. So this is the overall plan of what it should look like. One of the things that we will not do initially is to take all of the external networking that goes to CERN and sort of transfer half of it to Budapest. So we're looking at, in this particular picture, as basically the Vigna data center as another remote AS. So we will have normal layer 3 BGP between the two sites. So we'll really sort of separate it from a networking standpoint. We'll put a 10 gig IP service into the Vigna data center so that we actually have a good sort of extra sort of path that we can go through commodity IP to get there. And then we will have the two 100 gig circuits, as I mentioned, that will not only be path redundant in terms of fiber, POP redundant in Budapest, and actually POP redundant at CERN. So it will look like this rather large ring. Now, how that capacity will grow and what we will actually do with it will depend upon how we learn, what experiences we have, but it is entirely likely that 200 gigs will not be anywhere near enough capacity. So we may be growing this up as far as a terabit of networking between the two sites over the course of the years. But this will all be an evolutive sort of plan. We'll see how we go. We'll learn about it, and then we will plan accordingly. So there are lots of challenges, of course. Latency should not really be an issue, but for some types of services, it may become an issue. So this is again a learning curve that we have to understand. The networking is not so much complex, but there are issues with virtualization, moving virtual machines from one sort of network environment to another with the IP addresses. So we have to understand how we will deal with all of that. We want to actually keep the networking between the two sites as standardized as possible, but it does reduce some of the possibilities for how we can move services around. Nevertheless, this is rather an ongoing project, and we will build this up slowly as we understand how it all works. And we'll deal with issues such as the disaster recovery, what are the backup strategies for all of this, and so on and so forth. We do have disaster recovery policies in place today, but this will give us a whole new dimension of possibility for dealing with those type of issues. You shouldn't get worried, however. I'm not talking about creating black holes. That's okay. So the contract was signed. That's already done. During 2012, we will now issue the tender for the commercial part of the connectivity, and we will contract with Dante for the other part of the connectivity. We will grow that towards the end of this year, looking at putting in real production services. Q1 2013 is probably optimistic, but certainly between Q1 and Q2 2013 would be entirely reasonable. As David Kelsey mentioned this morning, I think that the accelerator is turned off at the end of this year for a period of 18 months for upgrades to run at full energy. So this will give us a window of 2013, 2014 to get a lot of these other projects in place and get all of this done. So we need to get the networking in first, of course. So that will start in the last few months of this year. First few months of next year, and then I think we'll be ready to start installing equipment probably Q2 in 2013. And then to be in full production in the first part of 2014, which will then give us a good year to have everything and all the operational procedures all robust before we restart the accelerator towards the end of 2014. That's it. Thank you very much.
I was caught out there. So, any questions for David?
Well,
I think we have a microphone on its way, Bill.
I can repeat the question.
How does it impact your software content? Is this just an extension of your land?
Right. So,
is it continuity of operation? Do you have to change your certain software architectures?
yeah, so I can repeat that. So Bill asked, how does this impact the software architectures, and do we actually have to make any significant changes, or is this just an extension of the CERN LAN? Well, it's not really an extension of the CERN LAN, as I indicated. The idea is that the data center will be in a separate AS, so it will be like a remote site. So we will sort of, we'll route between the two sites. There are issues around migration of virtual machines with IP addresses between such an infrastructure. This is something that we are looking at. We don't yet fully, I would say, have understood what we can do and what we cannot do in that space. So it's an ongoing project. Fundamentally, it should not have to change the software architectures. This would make it a much too costly enterprise. But what it does do is change a lot of our operational procedures, a lot of the way we handle incidents, the way we handle interventions, and that's been an area of major study so far.
Our physicists, is it okay?
Yeah.
Okay. Our physicists are very active, so I very appreciate that you will have a POP in the Budapest, and so I've seen on your picture there is a connection to ISPs. I believe that it would be possible to connect the dedicated line for the physical research. I mean, because we have currently our optical cables as a cross-border to the Bratislava. It's not very far to Budapest. So my question is, if it would be possible or not.
I think Lyle is right behind you. You should ask him. So what we did is we kept out of this the local connectivity politics inside Hungary with this. We just wanted to have the cost folded into the overall price for getting from the Géant POP to the center. So that gets us the basic connectivity. What you're talking about is something different. I think it's definitely not excluded. We've tried to keep the picture simple so far by having no external networking connectivity yet in Budapest, but this is just the starting point. Right? So this is just so that we can understand the complexity completely to get going. But I think what you're suggesting is something that would naturally evolve. Yeah.
Yes. Because from Prague to Geneva is quite far away, and so to Karlsruhe, which we are using for getting data from the experiment, so the Budapest is quite reasonable.
Yeah,
place.
I mean, you know, logically, you would imagine that you would actually want to have connectivity on both sites, and then that gives you some sort of, you know, potentially ring structure with cross-border fiber, with other things. So it gives you, you know, more of a network, really part of an overall network infrastructure. So I think there are many possibilities, and I think all of those things that you suggested are, you know, are things that we should discuss. And you know, once we get going in 2014, we can start to see how we can evolve this.
I think we have a question from Vasilis.
Yes, I would like to ask you if you considered, or if you're going to consider migrating into something like software-defined networking or open flow kind of strategies for your virtualized data centers, like what Google did 2 weeks ago or a month ago. They announced that they moved their virtualized data centers into some form of open flow environment globally.
Well, you know that that our on-site network engineers are quite conservative. So what they want to do is to put in place an infrastructure, at least for starting, that is very simple, very robust, very well understood. What you're talking about in terms of software-defined networking is really something that touches more of LHC1, which is the interconnection of open exchanges and how that can serve you know, the worldwide physics community. In that context, CERN is just another site, and certainly, you know, we are participating in that that overall SDN discussions that are going on in that context. So I think, in terms of the Budapest Center, it's a rather simple networking problem. You know, we will keep it that way to get going, but then the involvement of CERN in all of the, you know, the overall initiatives on SDN as part of LHC1, yeah, that's certainly going to continue. Yeah. I mean, there are many possibilities here, and you know, like everybody, we have a limited number of people and limited time. So we start off simple, and then we'll complicate it as we go along.
In the interest of timekeeping, I think I should probably thank David at this point.
Thanks.
And move on to the next speaker. So
thank you.
I think we're all well aware now that CERN and its LHC partners are one of the world's biggest networking users, certainly in the research and education community. I think now we're going to hear about perhaps a rival for that title, which is the square kilometre array. The presenter is Bill Johnson, who led ESNet for several years. And is still working there as an advisor and as a senior technical specialist. So welcome to Bill.
Okay, so first of all, let me emphasize that this talk, in spite of Roshin's involvement, does not represent what SK Project Office is planning to do. It is an engineering exercise in what are the parameters between different possibilities. And I'd like to say that there are 3 takeaways here. I couldn't upload my most current thoughts more than 30 minutes ahead of time, so they're not in the slides. First of all is that the onslaught of big data big science is continuing, and this is an example. The second thing is that the realm of very high performance networking is very much alive and healthy and will be leaking into our environments. The third takeaway that I want to convey to you, which I may or may not have time to elaborate at the end, is that the LHC data handling experience can provide very valuable lessons for emerging big science projects like the SKA. So, first of all, what is the SKA? It is a radio telescope consisting of several thousand antennae that operate as a single instrument. The square kilometer refers not to the size of the radio telescope, which is more like 1,000,000 square kilometers, but rather the actual sensor collecting area. So this is an enormous number of sensors. It, of course, provides a brand new astronomy capability, and in the process generates an amount of data that is significant even compared to the LHC. There are about 3,000 antennae, and it took me a while to understand that you don't call these dishes telescopes. They are not. These dishes are single pixel sensors, and in aggregate, the 3,000 of them form the radio telescope. The main site is about 100,000 square kilometers. There are 20% of the antenna and long arm branches that go out some 3,000 kilometers. This is an incredibly sensitive instrument and very, very fast, which gives it the capability of exploring new science areas. That is, it can scan the sky a great deal faster than the current telescopes. It has an impressive range of science, which you can read at your leisure if you're interested in the science aspects. There are a number of different kinds of sensors. There's conventional single pixel feeds, and this indicates the sort of density that one finds in what's called the core area, a couple of kilometers in diameter. In addition to the conventional single pixel feeds, they have what are called phased array feeds. These are effective. This is the same kind of phased arrays that are used in military applications. That is, it's a group of sensors, and by changing the electrical characteristics, they can effectively steer the sensor without repositioning it. And then there are these large aperture arrays. And I point out that these are distributed within an area that's roughly a bit over 300 kilometers in diameter, contains 80% of the telescopes, or the antenna, excuse me. There's a very particular arrangement of the geometric distributions of the antenna, and this is governed by the science characteristics that they're interested in. And then there's the data generation characteristics of the sensors, and particularly these array aperture arrays generate enormous amounts of data. This is per sensor, and so we're looking at an aggregate data stream out of here of some 15 petabits a second. Now, I have constructed this network-centric view of the SKA. This particular view, the reason for this will become a little clearer later on when I show you a similar image for the LHC. But the thing that makes this fundamentally different from the LHC is the distances between the receptors and the first layer of data processing, which in the LHC, this would be the first hardware trigger. But this correlator, which is the thing where all the feeds from all the telescopes go into the correlator, and then they're correlated in time and space in order to get the science out. These are on an average of 200 kilometers from the correlator. That means you have to have real networks in some sense that connect them. Then you have the output of the correlator at 400 terabits a second is still not science product data. That is created in a supercomputing environment, and this is likely to be 1,000 kilometers away. So that is, in fact, a wide area span of network. And then the distribution from the supercomputer center to the user community entails, there are only two places in the world that are candidates for this. One is the very dry desert area in southwestern Australia, and the other is a comparable area in South Africa. So you're talking about 13 to 25,000 kilometers to a distribution point that can then get the science data to the community. So the thing that caught my interest here initially was, how do you build a network that gets from the sensors? The microphone is falling off. How do you build a network that gets from the sensors to the data processor, the correlator? There was an initial desire expressed by the community that they should use standard off-the-shelf components and ones in which we had lots of experience and which were low cost due to mass production, which is, say, 10 gigabit Ethernet. And if you look at what happens with 10 gigabit Ethernet, you're talking about 300,000 to 400,000 optical components. You're talking about almost 1 million 10 gigabit DWDM channels. And in particular, when you look at both ends, you're talking about over 3 million network interface cards. That's a staggering amount of electronics. So the question was, first of all, how do we avoid using anything like conventional active DWDM systems? And we had discussions with Winston Wei, who's works for Neophotonics, which is a large manufacturer of what we call pluggable optics. And his response was, well, with these numbers, what you do is you integrate the optics module onto a custom NIC board. You use passive optical components in here with the exception of a dispersion compensation unit and some amplifiers. And then you do the reverse at the other end. He said with the kind of counts you're looking at for the network interface cards, such a custom integration is no big deal at all. The problem is in the counts of the equipment and even the passive elements that are involved. Then what I did was I talked to Kim Roberts at Sienna, and this is a greenfield engineering discussion that has no implications for, it's an optical engineering discussion. It's not a discussion of a Sienna product line or anything else. But Kim was very helpful. And he said, first of all, what you do is you go to 400 gigabit channels. This gives you a very nice reduction in component count. And secondly, he says you do away with Ethernet framing or any other kind of framing. This is a pure OTN solution. Any framing involved would just be defined by the forward error correction. He says you don't put any error correction or any error management at higher level. You rely on the forward error correction at the optical level to keep the path error-free. Now the problem with this was, when I first thought about it, was that, of course, for this kind of coherent networking, you have complicated modulation at the head end, which is not too difficult. But the demodulation at the receiving end is very sophisticated and currently only built into the high-end DWDM equipment. And like Winston Wei, what Kim said was, this is not a problem. You're talking about a sufficient number of components that what you do is that you integrate the optical receiver and the DSPs that do the demodulation and the forward error correction in a custom NIC card. And furthermore, you probably interface that directly to the data bus in the data processor. That is, you build this on a standard PCIX bus or something like that, and you write the data directly onto that bus. And so this is my comment about very high performance networking being quite alive and healthy. I mean, here you've got technology that is not that different from the 100 gig that we're deploying today. 400 gig is a little bit more sophisticated modulation, but the elements of this are sufficiently understood and modular at this point that you can take them apart and repackage them into a custom system. Oh, the other thing I should point out, this data is this is a unidirectional network. There is no return path. The reason for that is because there is no error correction, there is no feedback. If they lose a frame, the data from the sensors are probably even a higher percentage of noise than the data out of the detectors at the LHC. However, he's pretty well convinced that with the forward error correction going all the way back to the data buses of the sensors and of the correlator, that you're not going to get any errors. You're not going to get frame drops. And so what we've done is we've gone from 3.5 million NICs down to something like 85,000, and that's an enormous reduction of components. So that's the core area. That's this inner 300 kilometers to get from each of the to get from about 80% of the antenna to the correlator. The other big part of the network is the 1,000-kilometer reach from the correlator to the supercomputer center. The supercomputer center is assumed to be probably located in a town near the site. The problem with putting a supercomputer center on the site is that the other reason for choosing these particular sites is lack of humanity. And the significance of the lack of humanity is that you have to have perfect radio silence because there's many things that many of our technological gadgets generate RF in the frequency spectrums that are of interest to the telescopes. And so the correlator is built in what was described to me as essentially a submarine. That is, there's this welded steel room, which is a perfect Faraday cage, where all of the electronics are put. And it's probably not practical to put a supercomputer in that environment. And so once again, if we look at using conventional 10 gigabit DWDM equipment, this is beyond comprehension. I mean, we're talking about 200 fully populated DWDM systems. Imagine 200 Infineras or Sienna boxes. Every single channel is populated to its maximum capacity. By my guess, this exceeds the total amount of network equipment in every R&E network in the world combined. Okay? And so if you just look at the logistics of maintenance and operation, this is beyond anything that we have experience with. Once again, if you, Kim suggested, look, you do not need any of this. You can use exactly the same approach that was engineered for the pure OTN solution. You can dispense with all of the conventional DWDM equipment, and if you use special low-loss fiber here, you can go the 1,000 kilometers without regeneration. And so now what you have is you've eliminated all the DWDM chassis equipment, and you're left with something like 2,000 NICs as the equipment load that you're talking about. Plus of course the passive optical MUX/DMUX filters. So to recap, first of all, intuitively and actually in a crude cost model that I build up, the NICs are the dominant cost factor in this period, with the possible exception of the physical laying of the fiber itself. I should say, in this 300-kilometer core area, there's almost 300,000 kilometers of fiber. I mean, this is just there's a million channels converge on the correlator. Let's see, I think I commented about the OTN approach. This crude cost model gives, even assuming, as the neophotonics folks indicated, that you're buying in quantities, you can probably get the total cost of the Ethernet, 10 gig Ethernet channel end-to-end down to $200. You're still talking about $500 million in the cost of NICs. Whereas with the 400 gigabit, and you'll have to ignore the fact that somewhere here it says 400 gig E. It is not 400 gig E. I didn't have time to revise the spreadsheet that I cut and snipped into that. This is unframed. There is no conventional framing here. The cost is down by a factor of 20 or 30. You're talking even with designing a custom ASIC to do the decoding and FEC and integrating and building these boards. 2,000 to 3,000, 4,000 boards is sufficient that you amortize the cost very quickly. And I pointed this out. I think that if you look at the overall problem here, that I think that component counts are probably the dominant issue here because of the operational aspects of dealing with that many components. For example, if you just look at fiber management, I asked a colleague in a large commercial telecommunications company what was the largest fiber count that they had seen coming into any of their big co-location facilities in the U.S. And his answer was a 900 pair bundle. Well, that's not a drop in the bucket compared to what they're talking about in the inner area of the SKA. So even the fiber management equipment is beyond the scale of anything that anybody really uses currently. That doesn't mean it's non-existent, but that's a different story. Yeah, and using a conventional DWDM approach, not only is there a huge operational problem, there's an immense power consumption involved in this, and so on. And even using 400 gig E in a conventional DWDM system, you still have 11 fully populated chassis at each end, and perhaps a regen unit in the middle. And so this is, thousands of transponders to keep operating. And so, the point is that in spite of the allure of using, commodity off-the-shelf components, I think that there's an excellent case here to be made that that's not the right approach for a project of this scale. So I wanted to look at what the experience in the LHC tells us about this overall. So what are the similarities? The SKA collaboration, like the LHC, is going to be a large international collaboration involving science groups in lots of different countries. So you have similar data distribution problems. The science data replication or generation aspect of the projects are similar. That is, if you look at what comes out of the tier 0 at CERN and goes into the dozen or so tier 1 sites, it's about 50 gigabits per second, about 25 for each of Atlas and CMS. It's 100 gigabits per second for the SKA, comparable. It's also the case that the data is generated and sent to a single location, the T0 at CERN, for instance, and then distributed to the science groups. And I'll come to that model in a second. And then the data usage model, which has not been looked at by the project office. But if you think about it intuitively, it may be very similar to the LHC. That is, there may be a data set with, because you're taking, think of it this as continually generated images of the sky. People looking for different things are likely going to grab different pieces of this in a fairly random way. And so lots of different science groups are going to access the data to do their science. Now, if we look at the LHC in the same network-centric view that we had for the SKA, and actually this one came first, I want to reiterate several points that I made. First of all, for the LHC, this core area networking is just not an issue. The distances are short enough that this is machine room. I mean, this is at the detector effectively. This is a mix of analog and digital fibers coming out of the detector through the various triggering processes. This is still a very, very small area that doesn't require any special network consideration in particular. From the tier 0, the LHC model, of course, as I said, is that this data is, first of all, deep archived at the tier 0, and secondly, it is sent to the 11 tier 1 centers, and then in aggregate, the tier 1 centers hold a complete copy of each of the data. So there's some fraction goes to each of the tier 1 centers. And this network here, this is the LHC OPN. This is the private point-to-point network that was built initially to get the data from the tier 0 centers to the tier 1 centers. The tier 2 centers, initially the Monarch model that was developed at Caltech was a very hierarchical structured model, said that the tier 2 centers will be associated with tier 1 centers. They will get the data from the tier 1 centers in a very methodical way and then process it like that. Well, that didn't hold up. In fact, as most of the senior physicists with experience in previous experiments said, the tier 2 centers, this is the physics groups at universities who are doing analysis, they're doing the science on the data. They're going to pull data from anywhere they want. In particular, this will be driven by the kinds of hypotheses they're working on, and it will be driven by where they can most easily get the data, which incidentally may not be the tier 1 center, which is geographically closest to them. And so, in fact, that did happen, and this prompted, as that traffic, because in aggregate, the tier 2 centers, of which there are like 75 or so for each of the big experiments, in aggregate, they pull all of the data out of the tier 1 centers. So in aggregate, they're pulling 50 gigabits per second out of the tier 1 centers. And so as the hierarchical model started to break down and people started going everywhere, then this data started leaking onto the general purpose IP infrastructure for the R&E community. And particularly in the transatlantic case, that didn't work very well. And so this led to the LHC1, which I'm not going to explain in any detail, but it is effectively an overlay network. It's a VPN overlay specialized for science. And what it allows the participating networks to do is to choose the paths on which the data from the tier 1s to the tier 2s take. So they could basically they can engineer their network to accommodate this. And so that's what this fuzz on the tier 2 centers is supposed to indicate, that they'll get their data from anywhere. Okay. The lessons of the LHC, which I'm going to summarize very, very briefly, are that the science product is likely too large to have the working data set in one location. Certainly you do deep archive, and SK will do the same thing, but the technical aspects of building a centralized data repository with a mass storage system and a disk cache large enough in order to satisfy all the current request in an acceptable time, and the multiple high-speed, probably 10 individual high-speed connections coming into each one of those necessary to connect all of the tier 2 centers, and the political issues of concentrating all of the equipment of the collaboration in one place argues against a single large data center. And the model of the LHC in using the distributed data centers, the tier 1s, has actually, I think, worked very well. It decentralizes costs. It involves many countries directly in the experiment infrastructure, divides up the network load, et cetera, et cetera. regardless of distributed versus centralized, there's going to have to be an LHC OPN-like network to get the data from the supercomputer center to the distribution point and probably to whatever they use as equivalents of tier ones. I mean, that's a sufficiently concentrated use of the network that it will almost certainly be private links of some sort. It's probably also the case that an LHC1-like infrastructure will be used for the same reason, because you want to get the large amount of science analysis traffic off the general internet. And in fact, it may be that the SKA can use the LHC1 infrastructure that's being built. And so what we have is, if you look at the SKA data flow model, you've got a natural region in here which looks very much like the OPN, and so we have experience doing this. We understand how to build security policies for this kind of environment and so on. And then you have another layer down here at the bottom, which is likely to look a lot like the OPN. And the final point is on the lessons of the LHC, that all of which will have to be paid attention to by the SKA. Of course, TCP is a very fragile workhorse. TCP won't work at all for large international high-speed data distribution unless your networks are error-free, and you can't maintain your networks error-free unless you do extensive monitoring. And so the perf sonar infrastructure that's been put into place for the LHC, et cetera, you will have to have data workflow management systems to actually move the data. All of this has to be automated in order to get the kinds of volumes of data moving that are necessary to move. And a couple of us have written a book chapter that talks about this, a lot of these LHC lessons in some detail, and it's cited in the references. That's it.
Thank you very much, Bill.
Sure.
Have we any questions from the floor?
I may have to repeat the questions for me.
Okay. Well, my hearing isn't terribly good, so I might not be the best person.
That's my problem.
So we have one question from Vasilis over here.
Yes, very naively, Bill. I mean, do we still, I mean, I don't know, all the details, obviously, and, what are the requirements and so forth. I know that there is a very stringent latency requirement between the correlator and the sensors.
Yes.
But is there such a thing between the tier 1s and the tier 2s in this SKA environment? In other words, could there be a latency requirement that will make it more stringent than the LHC network?
No, I think that once the data gets out of the supercomputer center, it looks very much like the LHC data, and it will be processed in ways that probably don't make it latency sensitive at all. That's my understanding at this point. The power at the SKA site? So this is a requirement of the hosting country, and both countries have proposed running dual feeds to their power grids at 150 kV lines. I think the power consumption in the central area, if I recall correctly, is of order 50 megawatts, something like that, to run all of the telescopes. So it's large, but not huge. I mean, one of the reasons that the big supercomputer centers are located at the national laboratories in the U.S. is that historically most of those laboratories were involved in the project to develop nuclear weapons, and the old uranium purification techniques required enormous amounts of power, as did the old accelerators. So even an urban campus like Berkeley, we have a 180 megawatt substation. Oak Ridge in Tennessee has an 800 megawatt substation. So the 50 megawatt kind of power necessary to do this is big, but not extraordinary.
Just one more question.
Yeah, with the Australian and South African Pathfinder projects up and running,
Yes.
Do you expect to be able to extrapolate what they're doing right now with the much smaller Pathfinders and linearly carry that through? Are you thinking that we really need to see some new technologies developed in the 8 years before startup on the main SKA array?
So I know a little bit about the Australian Pathfinder project, and the answer is no, that will not in any way scale up to what's necessary for the full SKA. I mean, the SKA is designed to be built in sort of several stages. The first stage, which I believe is about 10% of the instruments, is intended to provide a look at the technology that will scale. And so that 10% of the antenna will be built in the first two, three years or so, and they'll use the experience from that to scale up to the full project. I believe that the Pathfinder projects they're doing now do not provide the kinds of scale necessary to extrapolate.
Yeah, well, thank you very much, Bill.
Sure.
So our next speaker, I must thank, first of all, for stepping in at the very last moment. The eagle-eyed amongst you may have noticed that Andrew Lyle was originally scheduled to give a presentation, but is unfortunately ill, so our wishes are obviously with his rapid recovery. But fortunately, Rodrigo Lopez, who is a colleague of Andrew's at the European Bioinformatics Institute, has very kindly stepped in and will give a presentation which is, I understand, a hybrid of Andrew's original and some additional material from Rodrigo himself. So,
thank you very much.
Over to you.
Yeah. Thanks. Okay, first of all, thank you very much for that, John. And again, I'd like to repeat what you just said. I'm here replacing Andrew, which is obviously quite a feat, also perhaps an honor. But I think the most important thing is that there where Andrew was going to describe the Elixir project in all its glory, my task in the Elixir is actually to implement it. So I decided to make a hybrid talk that talks a little bit about what Elixir proposed, what Elixir is actually doing, what we've managed to achieve so far, and where we're heading. So that's basically the nature of the hybrid talk I'm here to give you. So first of all, a summary of the talk. I'm going to have to, because you're not the usual audience bioinformaticians like me are used to talk to, I want to give you some definitions, a little bit about the terminology that we use in the field. Some of the terminology you will obviously be very familiar with, but perhaps some of it not. And we'll talk about some of the challenges that we're facing in that particular branch of biology and IT, as well as some of the technologies that are creating those challenges, but also some of the technologies that we're looking into using to solve some of the problems, some of the solutions that we are currently engaged in looking at, and then finally some conclusions and remarks. So in the context of the definitions, one of the things that happens to us all the time when we talk to an audience is people start talking about bioinformatics. I mean, tell me how I'm going to tell my grandmother where you work if you're talking about bioinformatics. What is that? And there are hundreds of different definitions. And perhaps the one that I'm more comfortable with is we're talking about biomolecular stuff. And biomolecular stuff in the context of bioinformatics is that computer representation of living molecules. And we're basically talking about bioactive compounds. We're talking about genes, which is something that many of you are perhaps familiar with. Genes are made of DNA. DNA has been plenty of times in the newspapers, in magazines, and so on and so forth. We talk about transcripts, which is what DNA does. Transcripts are the product of the message that DNA has, and how that turns into a living molecule. We talk about gene expression, which is the process that regulates how transcription happens. We talk about proteins, of course, about their structure, about their function. But importantly, in the context of bioactive compounds, we talk about drugs, which is a lot of what we do, a lot of what the academic industry are involved in the field of bioinformatics. Now, the interesting thing about all these things is that they all have a computer representation. That is where the informatics component in bioinformatics comes into the picture, and they're all computer-readable formats. Some of them are very, very old. The protein structure formats date back to the very, very late 1950s, which is very, very amazing. People were literally punching cards by hand there. Many of us were just simply not around at the time. And it's pretty amazing that in computational sciences, but in particular computational biocomputing, as it was called in those days, people were actually already using computers in the context of biology. Then the next thing is obviously web services. And this is not unfamiliar territory to all of you, I know. But we do a lot of that stuff. We do a lot of web services because what we do in biology and the way people consume tools and the way people consume data is most appropriately described as a web service. Not too long ago, in terms of years, we decided to adopt the technologies that the IT community were describing as web services, and we are very, very rich and very strong proponents of SOAP and REST. And actually, we've also been involved in the development of some REST-like protocols which are unique in the field, such as the DAS, which is used primarily for distributed annotation. So we are talking here about a development in the context of a protocol that we use quite extensively to share data with the communities. And obviously, you wouldn't go away from one conference such as this one without talking about clouds, which are also becoming very big, a very big component, but perhaps the core component of what we're doing today. But interestingly, there where we have been talking for years about clouds, about virtualization, about how to apply virtualization to the sciences, and applying for huge amounts of money to build our own computing facilities, we are now looking into leasing the stuff, no longer pretending to run it and spending our valuable research funds in building up very large compute infrastructures, but letting people that know about those infrastructures and then make a living out of designing, running, and selling services based on those infrastructures help us. Now, Elixir, what is Elixir? As I just pointed out in the context of the definitions, bioinformatics is a very wide-spanning area. And one of the problems bioinformatics has been particularly susceptible to is obviously funding. It's like many research areas, it is very easy to apply for funding for innovation. It is very easy to apply funding for an interesting research project, in particular if you're involved in health. But once you develop that particular strategy, once you develop a program, once you begin to hand over deliverables, you're left up with, and how do I run this for the next year? So part of the challenges, part of the big the challenge that Elixir is trying to address is sustainability. How can we keep that data, and how can we keep those tools useful, and how can we distribute those tools further to the community that requires them, not just for the duration of the project, but years beyond. So that's one of the big challenges Elixir is trying to address. In the first phase, Elixir was awarded about 4.5 million euro. We run very large feasibility studies with that money. I'll talk a little bit about that in the coming slides. But we're basically now in phase 2. And in phase 2, what we want is to go around identifying partners in various countries, and through those partners, engage in the implementation phase of a very large infrastructure for life science that will probably cost around in the region of about 500 million euros. So that is happening as we speak, and I'll go a little bit back to that in the talk. If you're interested, you're going to see that URL several times during this presentation, but that's basically the main website where you'll find both material describing Elixir for a research scientist as well as for administrative and political parties. Now, the challenges. One of the biggest challenges is obviously dealing with biomolecular diversity. We often talk about molecules as if they were perhaps incorrectly put, as if there were stars, but we know there are many different types of stars, and there are many different types of biomolecules. We're dealing here with genomes and genomic data. We're dealing with literature data. The literature is obviously very important. We're looking at nucleotides. We're looking at functional genomics. We're looking at expression arrays. I know I'm using a lot of geeky words here in bioinformatics. So I have to apologize a little bit for that. But we're looking at protein sequences, and sequences is what we refer to as the computer representation of living molecules in the case of DNA and proteins. We're looking at structures and protein families and so on and so forth. So this slide is basically just there to make the statement that we are dealing with huge diversity of in data. It's extremely heterogeneous, and it basically goes on from the very, very smallest thing you would imagine you see with an electron microscope all the way down to the single atom, all the way to an entire system, a complex living system, a complex living organism such as ourselves here. Following on with challenges, obviously, as technologies progress and the ability for us to get more high-resolution data from various types of instruments, the core biomolecular data is growing all the time. This particular slide just essentially exposes the growth that we've seen in recent years. So if you look at the nucleotide data, for example, which is currently undergoing a very heavy explosion, which is this first one here, it's basically in the span of the past 5 years that data has begun to grow very, very quickly as that technology has become very much widely adopted by various labs around the world. The number of genomes that we've sequenced in the past years is obviously multiplying very quickly. Gene expression experiments will tell us a lot about how disease evolves in living organisms and what are potentially the cures that we need to look into and the technologies that we use to develop some of those cures and some of those diagnostic procedures is also being used quite heavily. Protein sequences obviously are also growing. Macromolecular structure, so these are actually the three-dimensional representations of these living organisms, is also growing, although a little bit more linearly, and so on and so forth. So there's growth, actually quite a lot of growth happening in basically all the different types of biomolecules that we're working with. Disk storage, and I think people liked, well, in this type of conference at least, I've seen very big numbers being presented in the context of storage. If you see in this slide, it's for us also quite recent that we've been exposed to the very, very big storage paradigm and challenges associated with that storage. Just in the past 3 years, as you can see here, we moved very quickly from a landmark in our science of storing about 10 petabytes of data to just the end of 2011 with 16 petabytes of data. That's a huge increase to absorb, both in terms of the storage itself, its management, and our ability to cope with the technological challenges that we need to take into account to be able to deal with data and data processing demands. Right? Here we have a particular example of how and why this storage has become a challenge for us. The 1,000 Genomes project was proposed to produce about 1 terabyte of useful data, which is, you can buy 1 terabyte in a store today without anybody looking at you weirdly or anything. That 1 terabyte of data was actually what's supposed to be the output of dealing with about 100 terabytes of raw storage, which is at the time looked as a very sensible prediction. That was before next generation sequencing happening. Next generation sequencing is a technology that allows us to sequence DNA very rapidly in huge amounts. The 1,000 Genome Project obviously adopted that technology, was one of the early adopters of that technology, and right now we have about 9 petabytes of data being generated in one project alone. So that's quite a thing. Now, speaking a little bit about next generation technologies here, there are a multitude of instruments that can sequence DNA very, very quickly. Two of the most standardized ones come from two firms. One is called Illumina, another one is called Roche, who produce an instrument popularly known as the 454. And depending on which strategy you decide to use when you're sequencing DNA, you can literally ruin your entire university for all its available storage and potentially all its available funding, which is actually quite scary. And also, what is it that you're sequencing is very important. In the context of clinical studies, you would probably do something that we call for exome sequencing. So you're not interested in the entire organism, but you're interested in targeting a particular type of cell or a particular part of the organism's genome. If you're interested in much wider studies, then you do the entire genome, at which point your storage just gets blown out. Now, the other problem that we have is that it's not only us that are suffering from this phenomena. This map is essentially a representation, if you like, and I try to keep it very much up to date at the website called omics.com, which attempts to map where the major producers of next-generation sequencing instruments have actually sold successfully, and they know the machines are actually operational. The red dots here are where large number of instruments have been located, and those we like to call the major genome centers. There is a big cloud in Europe. There is also a big cloud in the States, and there's also a very big cloud in China, although I'm not 100% sure about how many instruments are still packed in the box in China, but I know their sequencing capacity is pretty major, so it mustn't be ignored. Now, what I'm trying to tell you here with this slide is that these machines produce huge amounts of data. And there is, in my view, sequencing overcapacity. The labs that buy these types of machines often do not realize the cost of running the machines. The machines usually cost around $500,000, something thereabout. To run a $500,000 machine for a year is probably going to cost you $2 million. But to buy the storage required to deal with the amounts of data that are coming out of these machines will probably cost you $4 million, which is absolutely unbelievable. So I'm not telling anyone here, or my colleagues at all, not to buy machines, but to put your samples in an envelope and send them to a friend that has a machine and has the storage to deal with it, get the good data back of him, and don't spend your valuable research money just buying a machine that is going to ruin you. And as you see here, there is practically every corner of the world is decently covered with machines. So there's always a good friend around that you can count on to be able to deal with your sequencing demand. This is our problem. We are major custodians of this data. And one of our functions is not only to harvest this data from all these laboratories, but to distribute it publicly and to give it to whomever they want. And in fact, the most important task we have is actually to help annotate that data, to give it meaning, to give it scientific meaning and relevance. This is our traditional gene archive, popularly known as a gene bank, if you like. And we've always been reasonably proud when we talk about that we have something like 246 million entries, and they're all perfectly annotated, and everybody comes and looks at them every day, and so on and so forth. But thanks to the new sequencing technologies, right, we're faced then of dealing with 2.2 trillion of these things, which is a huge, a big staggering number in terms of being able to not just deal with the data management aspects of dealing with such amounts of data, but in fact, how to keep it fresh and how to annotate and how to get the community engaged in helping us to annotate that. Now, this is a lot of geeky words I'm not going to go into, but these are basically things that are very, very important. RNA-seq and ChIP-seq and epigenomic data are extremely important in the context of medical studies and exploring human variation. And those are the types of experiments that are largely responsible for the explosion in data you see on this particular graph. The genomic and transcriptomics assemblies, which are submitted to this is the International Nucleotide Sequence Database Collaboration, which is composed of EMBL Bank, that's us over in Kingston at the EBI. Then we have GenBank over at the NCBI, that's the National Center for Information Technology in Bethesda in the US, and the DNA database in Japan. All this data you'll find in these 3 places in the world. at any particular time. So we do spend a significant amount of resources in networking and shipping data around to make sure that people in 3 different distinct parts of the world can have access to the data. And then obviously there's a lot of stuff coming from metagenomics. Metagenomics is a new thing, well, not quite new, but new enough to have become a very heavy producer of data, because it's through metagenomics that we're describing whole living systems. We're no longer sequencing single organisms or single cells or single tissues or single cells. We are sequencing entire water columns. We are sequencing entire ponds of bacteria. We're sequencing bits and pieces of brain and so on and so forth. Metagenomics is very, very important as well. Now, the other technology that is also responsible for producing a lot of data is in proteomics. You can get from DNA to a protein by using some sophisticated computing techniques to predict the sequence and predict the structure of the protein. That's fine. But you can also look at the protein directly. And that's what we call proteomics. There are 2 major initiatives running in the world. One that runs with us as collaborators, which is the PRIDE database. And there is also, as you can see here, a lot of data being produced from that experiment. One particular thing that uses tremendous amounts of space and tremendous amounts of processing when people want to do further analysis is where we're storing spectra. And we're storing the spectra from these molecules in actually very, very huge amounts. As I mentioned earlier, we are very much community-oriented, community-focused. We like people to tell us what they think. We like scientists to contribute to the annotations that we do. And we are involved in a project that is just generating comment. This is scientific comment. And very, very quickly, in the course of just 2 years, we've managed to generate 22 terabytes of comments from all over the world that help us annotate the proteomics data that are coming into the PRIDE database. The GPMDB database, which is similar, it doesn't propose to compete, but it has to philosophically a distinct nature, has also a similar problem, where they have huge numbers of residues, of 7 billion residues. They have a lot of redundancy, which I think is great. 137-fold redundancy is very good, because that means the data quality they can provide is quite high, and so on and so forth. So proteomics is another one of these technologies that is giving us a little bit of a hard time in terms of generating data very quickly. Now, why are we interested in this, and where again does Elixir come into the picture? It's basically its grand societal challenges, right? We've got, in Europe at least, an aging population, unsustainable food supplies, environmental destruction, terrorism, pandemics, and so on and so forth. And Elixir actually proposes a sustainable infrastructure to be able to deal with these things. Not only at this level, in the context of challenges, and of course, right now, business and commerce challenged by competitive pressures and globalization, a weak economy in Europe, and so on. But we're trying to ensure that we don't lose a track, we don't lose a focus on what can be provided as technologies that should be developed and that should create new opportunities and that should invigorate the economies to solve some of the problems that we're currently faced with. Right? Health and so on are actually very, very important. Now, the challenges, again, is access to data. And this is also quite recent. We generate a lot of compressed data, which is the way we get the data around. So we have 306 terabytes of compressed data delivered to about 1,500 worldwide core facilities. We use UDP, so we use Aspera actually quite a lot, in particular for the 1,000 genomes data, and we send around 110 terabytes of data per year to 20 core centers. But a lot of people want this data because obviously they want to be able to compare it with what they're doing in the lab. The data is generated quicker than it can be analyzed, and a lot of people never finish downloading a particular set before another one gets produced. So we're going in circles, basically. Disruptive technologies is basically the point I wanted to make here. I'm not going to spend any time there. I think I've spoke already plenty enough. Now let's go very quickly into solutions. 2004 web services is one of the things that we started working very hard in the context of various networks of excellence funded by the European Commission. Cloud storage is becoming actually quite big, and we've been looking at some of the commercial proposals in place since a little bit 2010, 2011. Our enterprise service bus is growing, integration via interoperability. And the focus right now, in between 2012 and 2013, both in the context of Elixir and the Biomed bridges, is giving scientists the possibility to bring their analysis software closer to the data. We are beginning to realize it doesn't make sense to attempt to move these huge amounts of data to the small lab. It's a lot easier to bring the small, large workflow to a data center, to a set of distributed data centers where the data is properly maintained. So we're looking into that. Like I said before, we are very keen and very, very observant, and we are also quite geeky. Our delivery, our cloud infrastructure, our cloud philosophy is based around the classical architectures that have been described in various talks here. We do a lot of SaaS, we do a lot of PaaS, and we are currently going into the EaaS a part of the business quite strongly. That's also thanks to Elixir. Now on the SaaS side of things, this is a graph of when we actually adopted web services technologies in the first instance and how that has had an impact in the community. There were before we had almost insignificant usage, although there was a significant investment in the compute resources. Today we're running literally millions of jobs per month, which internally translates into millions and millions of executional processes in our data centers, both in Kingston and in London. The same is the case in developing technologies as part of infrastructure to search this data. And we have several projects adopting that technology from not just around the MBOL, but around several partners, several international partners. I'll jump a little bit ahead of here, because I think the community aspects of this are actually quite important. We like to go and we like to talk to communities, and that's one of the reasons why Andrew and I are here, basically. We have invested a significant amount of time finding out how users need to have that data, how users are consuming the data, and what change we want to, we need to take into consideration in our planning. We've done multiple surveys and talked to a lot of people about this. We've actually even engaged with many of the people in that surveys in designing the systems with directly that feedback. This is not a nice compute experiment. It's actually pretty pen and paper oriented, but that is the way in which people communicate best, how they are consuming biological data at the moment, which is kind of cool. So we're using user-centric design a lot in the process of developing our interfaces. A conclusion so far, this is basically the last slide. Interoperability for us has become much more important than integration, being able to talk to others about how they're using the systems and how our systems fit into the grand picture. Measurements, as you know, in research, sometimes measurements are not in particular in granting. You'll get away with just essentially saying that the deliverable was that. That is not quite correct anymore. We need not only to store compute variables, but actually look at the working patterns of the users in order to be able to assess how the data is being consumed and whether that is the right way to use the data. User engagement and outreach are important, yes, as always, at a political level, but if you go and talk to users at the ground level, if you let the users help you design your interfaces, that turns out to be a very good thing. The challenge of big data in the context of this particular talk is, like I said before, is how to get the data closer to the user. And obviously recognizing the community is a big part of the solution, and that Elixir is already delivering in this. It was not sort of a grand plan to try to come up with a notion that infrastructures and sustainability for those infrastructures are important. What did the preliminary phases actually deliver? Actually, they seem to have delivered a lot, as we just recently got approval for a new building, which is going to be the Elixir Technical Hub, to be based in Kingston. This is a picture of that. The groundbreaking ceremony happens next month. And basically, this is the last slide. And what I want to point out in that slide is that as Elixir moves forward, next month, Our Director General and the Director of the EBI, Janet Thornton, who is the main engine behind Elixir, will be visiting Iceland towards the end of this month. And just to stop the talk there, I would just like to have a look at this, just very briefly. That's the live traffic from the European Bioinformatics Institute at the moment. And that is what's happening from around the world. Some sites we are having difficulties mapping because our mapping database doesn't have enough coordinates to map the stuff there, or maybe they are non-existent. The databases are pretty iffy things, but this is what is happening at the European Bioinformatics Institute at present. And we're dealing with something like close to 7 million requests a day for different data items, as I showed you before. I think I will stop there. I'm sorry I overstepped my time. I know you're dying for your coffee. That's it.
Thank you very much. Do we have any questions? One from Bill.
Yes, yes, indeed, and that is something that we are. Precisely, that's why we're here. That's one of the things that we want to discuss with you guys, and rather than attempt to reinvent yet another layer on the network scenario, we want to be able to see whether we can tap on your knowledge and perhaps actually tap on the networks that are already in place there, if that were possible. It's a common problem now for us.
How you manage data in sense of integrity, access control, and persistent identifier if you need it? And do you have also service linking the raw data to the publication or reports? What is actually required in the next European Commission?
We have both. And to answer your first question, which was about data integrity and access control and so on, that is all built into our systems. And there's just not enough time to tell you exactly what John was talking about, our colleagues in CERN, but we are running on tier 3 data centers in London. We're running on secure vaults, most of our systems, as we also deal with confidential data. Actually, this is patient data, so we're not allowed to distribute that throughout. We do have unique identifier spaces for each of the data types that I described briefly in my third or fourth slide. So I guess the answer to that first part of your question is...
Which data units you identify?
There are many data units. If we talk about...
So smallest to biggest?
If we talk about sequences, right, the smallest would be potentially just a tiny little peptide, maybe containing just 3 residues, and that's just a small file. That's basically very little, but it can have a lot of annotation. It can have a lot of annotation, so it might span perhaps into 5, 6, 7 kilobits of data in one. The largest one could be an entire chromosome, and that can get big. That can be several gigabytes big. So that, just speaking about sequences, if we talk about some of the data that we also store in the form of coordinates, for example, from a protein structure, that can be several gigabytes on its own for just a small one. And if we take that further and we look at some of the electron microscopy data that we're storing, that can go into several terabytes very quickly. We also store data in movies, so in gigantic AVS that actually describe a biological process over time. So yeah, there's a lot of heterogeneity in that. When it comes to storing the raw data, so we sometimes get asked to deliver to the users the raw data themselves. They like to do the analysis themselves, so maybe they feel that they can extract that last little bit of juice out of that data. We do that with selected people only, but we do, if a request is sent to us to do that, then we obviously engage with the right people to be able to deliver that data in some form to them. 2 years ago, we were faced with, could I please have a lot of the human genome data shipped over to the States? And it turned out the network was just not man enough to deliver that data quickly, so we had to call FedEx. Packed the disks, made a RAID 1 array, and gave it to the guy, put it on a truck, and fly it over to the States. Was much quicker than anything else. So FedEx has been a friend of us for a long time.
Are there any more final questions? No? Okay, well, I'd like to thank Rodrigo
No problem.
and all our other speakers today. I have a couple of announcements before the end. First of all, that the gala dinner will be tonight, and you'll be expected to make your own way there. You should have a map of how to get there in your conference pack, or there are additional